is Scott Fogel with Siemens Combustion Controls. I'm happy to be a part of this virtual FNA experience. I wish health upon everyone during these unique and challenging times. Thank you for tuning in today. I've been in the combustion industry for 9 years. Started my career working for a burner manufacturer. My experience started with learning about the burner, and now my focus is on the controls of the burner. Today, we're going to talk about burner controls for gas-fired heat treat furnaces. We're going to focus on the different methods to control the air and fuel to the burner. There are 5 different control methods that we will review. Fuel only, ratio regulator, parallel positioning, mass flow, and pulse firing. To be consistent with reviewing the different control methods, I will focus on 3 criteria. Temperature uniformity, particularly in reference to AMS 2750F temperature uniformity surveys. Fuel efficiency is a significant factor when considering the running cost of the furnace. Equipment cost will comment on the initial cost of the equipment. Below is my example furnace. This furnace perspective will help us visualize the different burner controls effect inside the furnace. As an arbitrary example, we have 4 burners on the left side of the furnace firing near the top, and we have 5 burners firing on the right near the bottom of the furnace. Here we have an example schematic showing fuel-only control. In terms of burner controls, we are only using a modulating gas control valve to control the amount of fuel to the burner. A firing rate modulation signal is sent to the control actuator, which increases and decreases the fuel. Fairly simple design. This curve shows the firing rate percent versus flow percent. For fuel only, we see the air is constantly at full flow and the gas is modulated based off the firing rate. Since the air is at full flow at all firing rates, there's a lot of excess air with this control. The downside of excess air is the system becomes inefficient. All the extra air has to be heated up to the furnace temperature, which takes extra fuel. The bigger the area between the blue air curve and the red fuel curve, the more inefficient the control scheme is. Coming up later, we'll see an efficient system which will have the air curve nearly on top of the fuel curve. One upside of a fuel-only system is high convective heat transfer at all firing rates. With all of the extra air going into the system, the velocity at the burner is high, which stirs all of the gas inside the furnace. This stirring with the extra air helps to make the temperature inside the furnace uniform. And looking at our furnace perspective, imagine each burner acting as a blender and stirring all the gases inside the furnace. Let's summarize fuel-only control. Fuel-only control is low cost due to the controls being simple and few components needed. This control is not efficient because we are dumping all the extra air in the system and has to be heated up. The upside of the extra air is all that stirring to get good temperature uniformity. We have now added a few components to our system for our ratio regulator control. We have introduced an air control valve and a ratio regulator. For modulating, we throttle the air control valve based on the firing rate system. We then have an air sensing line downstream of the air control valve that is connected to the ratio regulator. This sensing line links the airflow to the gas flow. When we modulate the air, the gas flow will follow, and we will maintain air to fuel ratio throughout the firing rates. Since we maintain the air to fuel ratio, this is where the ratio regulator gets its name. With ratio regulator control, the airflow and gas flow in parallel because they are linked together, or another term is cross-connected. We now see what an efficient firing of the burner looks like. The blue air curve is now right on top of the red fuel curve. The gap between the blue air curve and the red gas curve is inefficiency. We see the gap is minimized here, resulting in an efficient system. At high firing rates, we will have a large, hot, high velocity flame with a good amount of convective heat transfer in the system for good uniformity. One of the downsides of using a ratio regulator is that we have little stirring at low firing rates because the airflow has been modulated down. Imagine at low fire, we have several small hot flames firing into the system. These small flames have low convective heat transfer to stir the gas inside the furnace, which results in non-uniform temperature throughout the furnace. We'll go over some of the highlights of a ratio regulator system. A ratio regulator system is cost effective. We've added some components compared to fuel only, but the added components can typically meet a reasonable budget. Ratio regulator does provide a fuel efficient system, so the running fuel cost of the furnace will be low. Good uniformity can be obtained at high firing rates. The downside of this ratio control is low convective heat transfer at the low firing rates. Next control scheme is parallel positioning. With this arrangement, we now have a control valve on both the air and the gas. Based off of a firing rate, this control system will tell the air and gas control valve where to go. This system is an electronic air-fuel ratio control. We have quite a bit of flexibility with the air-fuel ratio in this system because we can electronically change the air-to-fuel ratio. The ratio regulator pneumatically links the airflow to the gas flow. With parallel positioning, we now electronically control the air-fuel ratio. The air curve looks very different. Looking at the curves, we now see that there are several markers on the curve at every 10% firing rate. Each one of these markers represents a setting of the air and fuel actuator at a given firing rate. Let's look at 50% firing rate as an example. At 50% firing rate, we can set the position of the air and gas valve. We can set the air control actuator to a position that results in about 60% flow, and we can set the fuel actuator to a position that results in just about 50% flow. We can adjust the entirety of the curve in this way. Since we're able to set the actuator based off of the firing rate, we can customize the air and gas flow to the burner. In this case, we're trying to burn efficiently at high firing rates by keeping the blue air curve close to the red fuel curve. At low firing rates, excess air is added. There is a trade-off between running efficiently at low fire and adding excess air at low fire to meet the temperature uniformity. We can keep adjusting the air actuator until a balance between fuel actuator and uniformity is found. This airflow percent curve with parallel positioning controls is a hybrid between a ratio regulator control and fuel only control. This system uses the advantage of a ratio regulator of being efficient at the high firing rates and good uniformity at the low firing rates, like a fuel only control system, all while trying to maximize efficiency. From the perspective of the furnace, we will have a large, hot, high velocity flame at high fire for good efficiency and uniformity. Then, at low fire, we will introduce excess air to achieve good convective heat transfer at the low firing rates. The key in this system is striking a balance at low firing rates of uniformity and efficiency. Since the actuators are being electronically controlled, the air and fuel actuators at a given firing rate can be adjusted to eliminate cold and hot spots during a temperature uniformity survey. For the cold spot in the top corner, the fuel actuator can be increased to add more heat to that spot, or the air actuator can be decreased to generate a hotter flame. Now let's look at the hot spot on the bottom corner of the furnace. The air actuator can be increased to cool the flame and cool the hot spot, or we could decrease the fuel to cool down the flame at that spot. Let's summarize parallel positioning. This control method is cost effective. Electronically adjusting the air-fuel ratio based off the firing rate is beneficial for optimizing for the requirements of the job. Can obtain good temperature uniformity by ironing out hot and cold spots by tweaking the air-fuel ratio. Let's have a look at a mass flow system. We now see an air orifice plate and a pressure transmitter on the air and the fuel. These pressure transmitters can be hooked to a PLC that take the pressure transmitter measurement and calculate a flow rate. Since the PLC control system knows the flow rate, the controls can all be based off of air and gas flow. The control system creates a set point for the flow of air and fuel. The control actuators will drive open and closed to satisfy the required flow measurement. In the other control schemes, we established a curve that resulted in air and gas flow based off of a firing rate. With a mass flow system, the flow can be customized by several different variables other than just firing rate. Let's summarize mass flow. Because of the orifice plate and pressure transmitter on air and fuel connecting to a PLC system, the system cost can be expensive. The result is high performance controls with the ability to customize for the job needs. The flexible controls result in good efficiency and making the furnace temperature uniform. The theme here is a high performing, capable control system with mass flow. The last control scheme we'll talk about is pulse firing. Pulse firing is unique in that the airflow does not modulate. Instead, the air valve cycles between two positions, high fire air and low fire air. When the cycle valve is at high air position, the air sensing line is connected to the ratio regulator, and the gas is increased. When the air cycling valve goes to low fire air, the ratio regulator will respond in kind and bring the gas to low fire. Air and gas flow are pneumatically linked by the sensing line. I've shown here a high-low pulse firing. There is an on-off pulse firing, where instead of the burner going to low fire, the burner is turned off. Instead of a curve based off the firing rate, we have 2 points the burner cycles between on our regular cycle time. As an example, let's say the cycle time is 16 seconds. At 50% firing rate, we'll have the burner at high fire for 8 seconds and at low fire for 8 seconds. Since a ratio regulator is being used, the efficiency of this system is good. There's minimal excess air being introduced in this system. Because of the regular cycling of the burner at high and low, the furnace gases are mixed well. Commonly, the cycle timing will be offset from burner to burner. As an example, let's stick with 50% firing rate, with 8 seconds at high fire and 8 seconds at low fire. The burners will be offset on their cycle time, which results in individual burners going to high and low fire at different times. Imagine inside the furnace where at different times the burners are going to high fire. This offset in cycle time is a great way to generate convective heat transfer inside the furnace and get good temperature uniformity. Pulse firing can have trouble with tight temperature uniformity at low firing rates. With 1 second at high fire and 15 seconds at low fire, there's not much convective heat transfer able to take place. Let's summarize pulse firing. Pulse firing can be a cost-effective solution comparable to ratio regulator control and parallel positioning. Since the burner is pulsing on ratio at high fire and low fire, the fuel is being burned efficiently. Utilizing the burner at high fire to generate mixing results in good temperature uniformity when load and temperature requirements are high enough to require frequent high fire operation. There are hybrid solutions that can combine multiple control schemes. Fuel-only control and pulse firing is one of those combinations. When the temperature set point is below a certain temperature, the system will control on fuel only, and then above that temperature would control off of pulse firing. Fuel only and ratio regulator combination is also possible. Thanks for spending time with me here today. My contact information is shown on the slide here if you'd like to reach out for additional conversation. Feel free to send in questions for the Q&A session. I'll be available for those questions. Thank you, everyone, and stay safe.